I really appreciate the ability to come in here as an archaeologist and a philologist and talk with the specialists in machine learning and deep learning. And so I'd like to share some of the cutting edge work that's being done in my field with the hopes that you'll, one, be exposed to digital humanities and data science intensive project taking place on campus in the Hearst Museum and with the D-Lab, as well as to get some ideas for where next steps might be, since this project's ongoing and we have made a lot of progress, but there's still a lot more to be made when it comes to developing optical character recognition for Cuneiform, which is not a Latin font, but rather made by wedges. So I'll get into that. But as you may know, archaeology in the Middle East and ancient Near East has a long and illustrious history with more than 150 years of Western academic scholarship from England, France, Germany, Italy, and the United States. And unfortunately, a lot of those discoveries inadvertently incentivized a pattern of looting and profiteering from the ancient sites throughout the area. It's a pattern that continues without end and without very much regard to the artifacts, to the data coming out of the ground. Still to this day, each season of ongoing excavations yields artifacts both monumental like these, as well as smaller artifacts that have writing on them. And in fact, quite a lot of writing is still emerging. Of course, these were taken into some of the major museums of our day, the British Museum, the Louvre, but that's not the policy anymore. And so many of the artifacts that are coming out of the ground kind of die a second death on the black market and then are kind of shuffled away into private collections. We can, following the news, see that this is actually one of the largest revenue streams for ISIS. They not only pull oil and gas out of the ground, they're also pulling artifacts out of the ground for a lot of their income. And so this is, of course, not just ISIS, before them Al-Qaeda, and before terrorist groups were doing this, of course, governments were doing this as well. So this is a process by which we need by which specialists and domain specialists can help the process by identifying what's coming out of the ground more quickly, so that they don't end up in, say, Hobby Lobby's collection, leaving the country entirely, ending up in the United States in a Bible collection. Unfortunately, this is something that continues to this day, where businesses and private interest groups or individuals can mislabel artifacts coming out of Iraq, in this case, as Turkish tiles. And then they'll very often go through customs, or at least certain countries' customs, even after being photographed. So this isn't that we don't have photographs of these objects. They do take photographs going through customs very often. It's just that there is very little in terms of recognition and identification of ancient artifacts compared to modern production of, say, tiles. So the main limitation is the human element. There's essentially 500,000 tablets that are indexed and known in the world, and likely that many unknown to us. And at least twice that much, it would be a good rough estimate still in the ground. But those numbers are, of course, unknown to us. So we can project a large number, but at this point we don't know. And there's really only maybe 500 experts working with the tablets who can identify when an artifact truly is authentic, coming out with cuneiform on it. And so most of the methods that we as scholars use involve taking a photo, if we're able to, if we're lucky, and making a hand-drawn transcription. So This is the first step of transmission or translation, a hand copy. Now, of course, hand copies and photos, both at this time, do not provide enough depth and detail for machine learning methods. At this point, we can recognize lines automatically with the number of photos that we have. And as you see, this is written horizontally, so those horizontal lines can be identified to some degree. But as you may or may not know, cuneiform is like a sign that's written, and these signs will very often be written very closely together. So carrying, if you're familiar with fonts, is variable and varies quite a lot depending on where it's and when the sign is written. Okay, so we're looking at methods for identifying individual signs on the tablet and connecting them with an already indexed Unicode code point for each sign. Of course, again, the 2D image just doesn't have the depth that we need. For that matter, we have moved into 3D imaging. Now, this is a costly and time-consuming process, but it's one that seems to be yielding better results for machine learning purposes, primarily because there's so much more that can be done with the image. And so I'm partnering with a number of universities and museums and ongoing excavations to try to build up a data set for this. And I'm going to explain a little bit about where the method is at this point. So on the left, the 3D image goes through a software that uses segmentation, where they rasterize and vectorize an image and attempt to create a minimal skeletal representation of the sign. At this point, you can see the output of the 3 top signs recognized, and the kind of as it's read horizontally and vertically, what we can gauge are the dimensions of a sign. Now, there's about 1,000 signs in total for the 4,000 years of written history. But if we constrain that to, say, a specific group of texts that are written in a specific area, then we're looking at something more like 150 signs. So these need a certain amount of specialist knowledge to train groups of tablets for their lateral and vertical readings from the tablet as they're read across the 3D surface. But we also are working on matching those then, matching the output that we receive from the model to the standard wedges. And there are about 4 different directionalities of a wedge. Each wedge, horizontal, vertical, and diagonal, is more or less kind of standard form. They call it the gestalt of a sign, which will remain constant over time, but varies, of course, with handwriting styles. Not as drastically as, say, calligraphy, because calligraphy is done with a pen, whereas cuneiform writing was done with a wedge writing instrument, a reed stylus, that was cut into 16ths. So the standard writing system kind of imposed constraints already that are helpful for us. But we haven't gotten to the machine learning part of it, primarily because we don't have a large enough data set of 3D images. What we do have are a lot of 2D images, about 500,000 of them. So the idea is currently to try to pair what we're getting from these dense 3D models with the 2D images, and through this process create a large training set for both data set types, 3D and 2D. But for those familiar with OCR, you usually need hundreds of thousands of examples in order to get the correct matching in the rasterization process. So we're currently working on this method of recognizing individual signs in the different directionalities. And the process looks promising. And this is why I am interested in it and working with it as well. The software is quite intuitive to use as well currently, GIGA Mesh, and works on Linux the best. Basically the gist is that it uses a way of marking the depth of each sign in order to create that kind of form, the gestalt, again, of each character, of each wedge. Now the devil of the task, of course, is again the caring. So when does one sign edge or one wedge pair or group end and the next begin? So we're using supervised scholarly input in order to, and the Unicode code points as well, in order to create kind of acceptable groups so that there can be a kind of matching that takes place. And we are using feature to vec, or wedge to vec, if you will, and dimensional space in order to chart the directionality of the wedge, because of course in any model or photo you may not know if it's right side up or upside down. So if you, and a computer wouldn't either, and so as it's fed in, it needs to be able to orient itself to the correct orientation of the signs through the wedges themselves. This is incredibly challenging, even from the 3D model. So we're using a lot of supervised input from Assyriologists, scholars who write Cuneiform, who are writing the copies by hand still. And we're doing that with SVG output so that we have overlap over the corners of the wedge. So we're kind of taking like a multifaceted approach, one that it takes in as much domain specialization as possible and pairs it with what we can glean from machine learning methods, and hopefully in the future deep learning methods when we get our data sets bigger. So again, we kind of walk through this pipeline, and where we're at currently is in categorization methods, again trying to build up large enough repositories of pairings from a Unicode code point, a rasterized image, and the vector representation. But of course, deep learning is a game changer. So if it turns out that we do end up with, say, somewhere along the lines of 100,000 tablets in the near future, then that would change the methods to some degree as well. And yeah, that's currently where we're at in the project. So I would definitely be interested in any input you may have, any ideas, or in general, just to spread the word that this is happening here at Berkeley. And we are definitely interested in looking for methods that are novel for optical character recognition when the characters fall outside of a standard set. And last but not least, like I said, here are the partners we're working with. Of course, the Hearst Museum is allowing us to scan 1,000 of their tablets. The D Lab is helping us with the machine learning support, as well as Heidelberg University, which is developing the GIGA Mesh software. I'm so far partnering with excavations taking place in the Middle East where tablets are coming out of the ground. And the Prague University and other universities in Germany are using this method as well. So it's kind of an ongoing process to recognize the impossible image at this point. Thank you very much.
We have time for 1 or 2 questions. Okay, first question from Henry.
I might have missed this, but I'm just wondering, do experts know the meaning of the language? Can you just read it? And if so, what does it say?
Yeah, we do. So basically, there are a number of languages that use this writing system. It was in use from about 3000 BCE until 45 AD. It kind of got. It was still we'll still find bilingual inscriptions where there's like Greek that was like carved into the clay on one side, and the cuneiform wedges pressed into the clay on the other. But the medium at that point was shifting as well, so that clay was no longer the standard, and it was moving into paper. And so cuneiform makes no sense on paper, except for the modern scholars who are using it. But basically, there were a number of languages that used that writing system, beginning with Sumerian, actually beginning with Proto-Elamite. That's still being indexed in Unicode code points, right? And not there yet. But Sumerian and Proto-Elamite, these kind of southern languages around 3000 BC in southern Iraq and southern Iran. And then it moves mostly into Iraq, Syria, and Turkey over time through the Akkadian language, which represented the dialects of Assyrian and Babylonian. And then you have Hittite, the first Proto-Indo-European language, perhaps, was written in cuneiform. Even the pharaohs during the Amarna period in Egypt were writing in cuneiform to communicate with the larger world, although hieroglyphs are more their thing. And then you have the first alphabet was also written in cuneiform, Ugaritic. And these early alphabetic scripts were just kind of a simplification of the cuneiform as well, along with hieroglyphics that became kind of influential in developing alphabet scripts. So this more or less was like I wouldn't say lingua franca, but like the main writing system for at least 2,000 years. Unfortunately, those cultures died and collapsed, and so we didn't know they existed until we rediscovered them. And there's, like I said, just like we're at the tip of the iceberg in terms of the data that we have currently, and there's like civilizations still under the ground that we're only now becoming privy to because of looting and excavation in the area. So it's a big data set. It's just not out entirely.
There's a hand up here. I guess we have the question here.
Yeah, quick question. I'm just wondering. First, great talk.
Thank you.
I want to understand the level of variability of this. I mean, if OCR on handwritten is difficult,
yeah.
These cuneiform glyphs on sort of mud, right?
Yeah.
It might be incredibly complicated. How much it varies? I mean, a single glyph, how much it can vary?
That's a good point. That's a good question. Quite a bit, honestly. I have a slide that maybe can show a little bit of that. There's, let's see, here, for example, this is just one, whoops, I have to unhide it in order to display it. Okay, but you can see here that, so beginning in the very early period, we find logographic depictions of the sign. So this is the sign for head, and you can even, you can see very much like it's like an emoji, basically. And then as it became more formalized in the writing schools and the more or less the academy of the day that became what we call university, these signs became more and more abstractivized from the original. But you can see, even in the late Assyrian, late Babylonian periods, there's still some resemblance to the early form, and that's over 3,000 years. So the challenge, of course, is that the number of wedges, changes depending on the region and the time period. And so again, as a specialist in Assyriology and learning the data science as fast as possible, I realized that this isn't going to be kind of like very generalizable until we have a really large data set. So instead, we're going after very specific kind of textual communities. that were very prolific. So the Ur-3 Sumerian period was very prolific. There's already in online databases around 100,000 tablets, and those we have primarily just through looting. So there hasn't been a lot of excavation of that region, but now it's opening up for that. So I imagine that with proper excavation, that number of about like 150,000 tablets will probably triple, because we'll actually discover the areas where writing's taking place. So more or less, to answer your question, there's a ton of variability. There's a ton of it. The beauty of it, of course, is that all of these are wedges. So that unlike a calligraphic writing system or you know, where there's just infinite variability in how you would write a letter, this has the number of wedges may change, but again, the gestalt of it, like the kind of wedge groups, end up resembling something similar. And then, of course, we have about 100 years of scholarship telling us which of these groups of signs belong to, you know, a sign name, let's say, like a one. So there's a lot of categorization and typology that's taken place through specialist knowledge that we can leverage in this process. It's just a matter of building up a comparable data set at this point where we can then map those collocations together and kind of. So I'd use a lot of like network analysis. So we're definitely using like bimodal networks in the process, because all of this has to be supervised at this point, supervised learning.
So we have one more question here.
Thank you for the great talk. I wonder what is the size of the data sets that are labeled, or maybe some transcriptions that probably don't have corresponding plates scanned yet, for, let's say, major language and period.
Yeah. So right now, online databases, which very often will include a photo of the object, are in like a transcription language. Let's see, like I was showing here, they would say for this sign, ka. So they give a reading for it. Now that's a form of a label that also corresponds to a Unicode code point. And for that, we have about at least 400,000 tablets that are indexed by a transcription, meaning like for every sign, there's a corresponding label. Now, from the 3D data set, we only have about 400 tablets from the Jena University. There are many more tablets that have been scanned in 3D by the British Museum in Louvre, but those data sets aren't available because the technology is kind of new and they're worried about reproduction issues, like reproducing the tablets and selling them and things like this. But the hope is that as we kind of develop best practices for capturing 3D or creating 3D models of the tablets, we'll create like an online index of which tablets have been scanned, and we'll then use these online databases that are already transcribed, meaning for every sign, again, there's a label. So it's kind of, I would say the task has been largely done in terms of labeling the data sets. It's just a matter of developing a comparative data set that is rich enough for the rasterization, vectorization process, because a photo doesn't do it.
Leads me to the question how that can inform imposing the priors from, let's say, the sequence of the characters, how that can inform. Probably you talked about it in a way, how that will inform the information and providing priors to.
Yeah, so currently, like the method is, we're working on using the kind of like network analysis process that will take in the 3D, so the kind of a space in which the same sign in 3D is rendered in a 2D image along with the Unicode code point and transmission, so in a database. So again, it's like a supervised method because we don't have data sets large enough to kind of create the rules and let it learn itself yet. But the rules are all very well established. It's just a matter of kind of drawing the connection between the, the space here, let's say, on a 3D image, to the sign form as a scholar has recognized it. So kind of creating equivalency tables between these two, the specialized and the kind of visualized form. And this has only been done so far for maybe 200, 300 tablets. So that's pretty small data, basically. Each sign, or each tablet may have anywhere between 10 and 50 signs on it. And yeah, so it'll be a slow process. Even though we have a lot of images, unfortunately, they just aren't very good for training purposes, or for OCR yet. Too much loss in the rasterization.
So let's thank our speaker, Adam.
Thank you.
And actually, let's thank all of our speakers for ImageXD from both yesterday and today in our tutorials on Wednesday. You make ImageXD possible. So thanks to all of you. So I think I'm standing between you and food, so I wanted to make sure that I let you know. We have lunch scheduled until around 1:30, starting right now. And then at around, it's not 1:30, I'm sorry, 1:10. And around 1:10, we have time for hackathons and collaborative work. So there's some talk about the lightning talks. We currently have them scheduled for 4, but heads up, we might want to push it up to see if people can talk about this a little earlier. So we'll announce that in a bit, but in the meantime, lunch is served, and we hope you enjoy your meal.
Well, let's just check in quickly because I'm not sure everyone followed. So, who's planning to stay around until at least 3 this afternoon? Okay, and who's planning on leaving sort of around the end of lunchtime? Okay. What's it? Yeah. So I guess we can. So it looks like the majority of people will stay at least until 3. So if we do the lightning talks at 3, most of you will still be around, I think. All right. So yeah. So shall we do them then? Yeah. Okay.
Awesome. One last thing is you're welcome to